Welcome to The Explainer. Today, we're diving into the secret behind the incredible strength of things like jet engine turbines and even your car's chassis. It all comes down to a simple fluid bath, a process called quenching. But what happens when that crucial fluid starts to get old? And, more importantly, how is AI helping us spot the invisible signs of failure before disaster strikes? Let's get into it. So here's the big question, right? How do we get metal parts tough enough to handle the insane forces inside a jet engine or the constant beating a car's frame takes? Well, the answer isn't just about the metal itself. It's all about a pretty violent and perfectly timed cool down that literally locks in its toughness. You see, it's not just about the heat. It's all about nailing the perfect, and I mean perfectly consistent, cool down. Picture this. You heat a metal part till it's glowing red hot. Then you plunge it into a liquid bath to cool it down in seconds. That shock, that's what we call quenching. It freezes this super strong molecular structure right into place. Now, if you get it right, you get almost superhuman strength. But get it wrong, even by a tiny bit, and you've created invisible weaknesses, the kind that can lead to catastrophic failure way down the line. All right, so let's get into what really makes for that perfect cool down. Because as it turns out, the speed of that temperature drop is absolutely everything. And controlling it, well, that's both an art and a science. Okay, take a look at this graph. This is what's called a cooling curve. And you can think of it as the unique fingerprint of a quenching fluid. It shows you just how fast a part cools down over time. Now, what's really important here is to notice the difference between the solid line, that's brand new oil, and the dashed line, which is the exact same oil after it's aged a bit. See that? The performance, its whole fingerprint, has completely changed. And that means the parts you're making are going to be different and totally unpredictable. So that changing fingerprint we just saw, it points to a really fundamental problem. These crucial industrial fluids don't last forever. We're talking about a fluid's slow decline. It's this gradual, almost invisible decay where they're constantly degrading and changing in ways that are just incredibly hard to keep track of. And this process has a name. It's called quenchant degradation. Basically, it's the gradual breakdown and contamination of the quenching media. It alters its cooling performance and, you guessed it, can lead to a whole bunch of defective parts. You know, day to day, you might not even notice the change, but over weeks and months, that's the hidden culprit behind parts that are too soft or warped or even filled with tiny microscopic cracks. And what's causing this degradation? Well, it's coming from all sides. For oils, it's a chemical thing, oxidation, from all that heat and air plus contamination. For polymers, it can be purely physical. The pumps can be so violent they actually shear the long polymer chains, just breaking them down. And for pretty much all types, you're fighting a constant battle against the buildup of sludge, carbon, and all sorts of other gunk. And here, this is what that looks like in the real world. This pattern is called soft spotting. It's a defect you get when contaminated fluid causes one area of the part to cool down slower than the areas right next to it. And believe me, this isn't just a cosmetic issue. We're talking about a deep structural flaw. It is, quite literally, a failure waiting to happen. So if these fluids are constantly and silently degrading, how on earth do manufacturers fight back? Well, this brings us to the promise of prediction. They're turning to the power of data and artificial intelligence to try and predict the unpredictable. I mean, look at a system like this. To manage something so complex, factories are embedding sensors absolutely everywhere. They're monitoring everything in real time. We're talking temperature, flow rates, pressure, viscosity, you name it. The big idea is to create a complete digital picture, a kind of health report for the system that's updated every single second. And all that sensor data feeds right into an AI-assisted workflow. So first, software safely pulls all those signals from the machines. Then, that real-time data gets fed into machine learning models. But here's the really clever part. They often start out in what's called shadow mode. This means the AI is making predictions in the background, testing itself against what actually happens to make sure it's accurate before it goes live. Then, once it's validated, it starts helping the human operators, giving them insights and acting like a super-powered early warning system. So with all this data and all this amazing AI, the problem of aging quenchants is solved, right? I mean, it sounds like the perfect solution, a system that can see problems coming and warn you before you ever make a bad part. But as it turns out, the real world is, well, it's often a whole lot messier than the data makes it. And that brings us to our next section, when algorithms go blind. See, The problem is that an algorithm only knows what its data tells it. And we're about to see some really subtle but absolutely critical ways that these super advanced systems can be completely fooled by the messy reality of a factory floor. A lot of the time, the trouble starts with the sensors themselves. The very things that are supposed to be providing the data. As this quote points out, many commercially available water and oil analyzers are subject to frequent malfunctions. And that's the key right there. In these super harsh industrial environments, sensors can fail, they can get clogged, they can just stop working right, feeding the AI bad information from the get-go. Just look at these classic examples of what can go wrong. On one side, you have what the algorithm sees. Maybe it sees a stable polymer concentration, because that's what the refractometer is telling it. But what's really happening is that a bunch of contaminants are confusing the reading, and the actual polymer level is a total mystery. Or, here's a good one, the algorithm sees the pump motor is on, so it calculates the fluid velocity and thinks everything's great. The reality? The propeller has literally fallen off inside the tank, so there's actually zero agitation. The AI is completely blind to it. You see, the real world is messy, and the data we collect can be a misleadingly clean reflection of it. This just highlights this massive gap between the digital world and the physical one. You've got this clean, orderly data model on one side, and on the other, you have the messy, greasy, totally unpredictable reality happening inside the machine. An AI that trusts the data alone, yeah, it's flying completely blind. So if pure data isn't enough, what is the answer? Well, this is where we move towards intelligence, not just automation. It's all about realizing the goal isn't simply to automate everything. It's about creating truly intelligent systems, where machines and people work together, each one covering the other's blind spots. The goal here isn't to replace people, but to empower them. Think about it. When you have an AI system handling all the tedious, constant, 24/7 monitoring, it frees up your skilled operators and engineers to do what humans do best. Analysis, creative problem solving, and actually improving the process. The AI becomes a tool that elevates human expertise, not something that makes it obsolete. And this is being driven by a really powerful new approach called machine teaching. It's a process where industry experts can embed their own domain knowledge and experience directly into the AI models. So instead of an AI trying to learn everything from scratch, which takes forever, a human expert can step in. An experienced engineer knows that, hey, that specific sound from a pump usually means a pressure drop is coming. They can literally teach that rule to the AI, making it smarter, way faster, and aware of the context that isn't just in the raw data. And this really is the key takeaway. The most effective systems, the ones that are truly going to work, are the ones that combine the predictive power of AI with the irreplaceable domain expertise of human operators. You get the best of both worlds. The tireless, data-crunching consistency of the machine, paired with the adaptive, context-aware wisdom of an experienced person. So this leaves us with a final, much bigger question. As our technology gets smarter and smarter, how do we make sure it also gets wiser? The real challenge isn't just about building powerful algorithms. It's about teaching them to understand and even appreciate the messy, unpredictable, and kind of beautifully complex world that they're actually meant to serve.